Hello guys, and welcome back to my channel Civil Construction and Tutor, and in this video we will be designing different types of footing based on loading magnitude and site conditions. That is isolated footing, combined footing, strap footing and mat footing, or we can say wrapped footing. So without further ado, let us start. So here you can see the building is supposed to be constructed on this side. So this is the area of the building. So I have provided combined footing, strap footing and isolated footing. So firstly we have to understand that the footing is designed on the basis of the load as the reaction from the ETABS, and on the basis of the reaction we select the size of footing and analyze it on SAFE. So this is SAFE 2016. We will model footing in this and we'll check whether it is safe or not, and the working principle and the ribbon and the graphic, the windows are somehow similar to that of ETABS, so it will be easier to understand if you have already worked in ETABS. So file, and we'll go with new model, design code, as we are using IS code, so IS 456-2000. Design preferences, you can go here and select design code over here as well. Minimum cover slab, so for footing it is generally provided as 50 mm as it is in direct contact with soil, so there might be presence of moisture. Preferred bar size, so for general footing, that is for isolated footing for residential building, it is generally provided as 12 mm. Minimum cover, so it is for strap beam, we'll do that later on. Okay, project information, if you want to add the client name or anything. Units, will consider metric default. Okay, now let us go with blank. I have selected blank to make sure that you will understand how to make a grid for all of the footing types, that is either that is for mat footing, combined footing, strap footing, so it will be easy to understand. Similarly, go to define materials type. It is similar to that of ETABS. Add new material, so material name will firstly define for concrete, so let us assume M20 grade of concrete. Then it is concrete. Wait for unit volume, so for concrete it is 25. Similarly, modulus of elasticity, you can compute this as 5000 into square root of the grade of concrete, so for now it is 20. Poisson ratio 0.2. Thermal coefficient of thermal expansion, this is 0.000000055, and similarly specified concrete compressive strength for 20 grade of concrete, it will be 20. Okay, so similarly we can do for the rebar as well. So let us take FE 500 grade of steel, so it will be material type as rebar, and it is 76.8. Modulus of elasticity 2 into 10 to the power 5. Minimum yield stress is 500 and minimum tensile stress is 545. Okay. Similarly, let us define the slab property. Add new property, footing. Let us assume as 400 mm. Go for M20 grade of concrete. Select type of slab as footing. Then thickness we are considering as 400 mm. Thick plate, as the slab thickness is considerable in comparison with the dimension of the or span of the slab of the footing. Okay, so in real structure there is an extremely stiff region within the connection which joins the column and walls to the slab, and we have to assign that particular region in the slab for designing the footing. So we'll add a new property that will be defined as stiff. The material type should be same as that of slab, and it is selected, or the analysis property data is type as of stiff, and the thickness will be same as that of the slab thickness, and it will be a thick plate as well. Okay, so slab property has been defined. Let us define, if there is strap footing, then we'll define beam properties. Soil subgrade property, as the footing rests on the soil, so we have to assign soil subgrade for that particular footing. So modifier slope property and subgrade modulus compression only, as we designed this soil for compression only. The value of subgrade modulus is computed by using simple formula, that is soil bearing capacity into factor of safety into 1 by allowable settlement. For now, soil bearing capacity is taken as 110 into factor of safety from the geotechnical aspect, it is taken as 3, and allowable settlement is taken as 25 mm for isolated footing and 50 mm for wrapped footing. So we can provide this as 13200 kilonewton per meter square per meter. So this is the value of soil subgrade. Now let us apply this value. So we can calculate that value here as well. 110 into 3 into 1 divided by 0.025. So 13,200. Okay. Similarly, load patterns, dead load, live load. So dead load includes the weight of the footing itself. Live load is not to be included here as we are taking the Coulomb reaction directly. So firstly, let us go to ETABS and understand how the reaction is extracted and what are the load combination that has to be considered for the design of footing. So this is the ETABS file of that building, and here you can see I have already analyzed this building. So I'll just take the reaction. Now basically for the calculation of the size of foundation, we consider unfactored reaction, that is dead load plus live load only. So you might wonder why we are not considering any factor of safety for calculating the design of or size of the foundation. So it is simple, because the foundation will never receive a greater load than that of the value we are assigning, that is 1 times of dead load and 1 times of live load. And similarly we can also consider the geotechnical aspect, that is while considering the or while calculating the allowable bearing capacity, the geotech engineer considers a factor of safety, and that is why we are already in the safe side for calculating the size of foundation. So it will be uneconomical if we enhance the value, that if we consider a factor safety while calculating the size of foundation, because the geotech engineer has already considered a certain factor of safety for calculating the allowable bearing capacity. Also, if we see, we have considered dead load and live load, but we haven't considered earthquake load or wind load. Why is that? So simply, this is also explained in the IS code. You can find this in IS code 1904 clause 15.1.5. 1.6. So where wind load or seismic load is less than 25% of that due to the dead load and live load, it is not to be considered in the design, and we have to design it for the first combination, that is dead load plus live load. So what is 25% over here then? For this you have to understand IS 1893 part 1 2016. So for the calculation of the base shear design, which is actually the earthquake load, we have VB is equal to AH into W, and W is the seismic weight, and seismic weight is simply dead load plus live load. And the code has said the earthquake effect should be 25% of the dead load and live load. So that means this is the coefficient that the code is talking about. For general building, let us see in our case. Let us go to, as we have already analyzed, we go to display and show tables. We'll see the base shear coefficient in the load patterns definition, load patterns, and in the load pattern definition, autoseismic. So you can find that value over here, and it is 0.09, that is 9% only. And the code has said the value should be greater than 25% in order to consider the seismic effect, but for now the value is less than 25%, so we can neglect the seismic load for the design of foundation. So that is why we are considering dead load and live load only for design of the size of foundation. In the load combination, I have added one combination manually, which is for the dead load and live load considering scale factor 1. I will check the reaction for this load combination. Okay, let's go for the plan view, base, apply, and go to display, force or stress diagram, support or spring reaction. You can find that over here as well as a shortcut key. So we'll see the load case or load combination for the combo reaction, and we'll see for the FZ, MX and MY. Apply. So these are the base reaction for the building we are considering, and according to this the size of the foundation has to be considered. And in general building or in general residential building, the value of moment is significantly less as compared to the axial load. Hence in many design the moment are neglected while designing the foundation. So here you can see the value as 6, 1, 4, 5, and if we compare it with the axial load, which is 300, 400, so we can neglect this value for design of the foundation. Firstly, we can see that the loading magnitude determines the type of footing and the size of footing, As the spacing between these two columns is 3.6 meters, so we can go for isolated footing as there is significant space available and there is less chance of the overlapping of the pressure bulb. So what is pressure bulb? So simply a pressure bulb, also known as isobar, is a stress contour or a line which connects all points below the ground surface at which the vertical pressure is same, and we should consider this for the selection of the footing as well. That is, the isobars or the pressure bulb of two different footings should not overlap with each other. So when two footings or two isolated footings are close to each other, then there may be a chance where the pressure bar or the isobar can overlap with each other, and that is to be avoided. So now let us design the footing for one of these corner columns considering the maximum load. So now let us take this 171.9254, and with respect to the vertical load, we can compute the area considering the soil bearing capacity. So I have made a simple Excel file here. So service axial load coming from column, which is 171.9254. So let us assume this as 172, and soil bearing capacity, this depends upon site condition. So now let us take this as 110. Area required for footing can be computed as service load plus self weight of footing divided by P allowable. You can find this in IS code as well, in IS 1904. So here you can see, determine the required bearing area. So service load, which is 172 kilonewton. Similarly, we have to consider the self weight of footing, that is the concrete that is going to rest on the soil. So generally it is taken as 10% of the service load as the self weight of footing. So let us take this as 10%. Now area of footing required, that is 172 plus 0.1 into 172 divided by 110 kilonewton per meter square, we get 1.72 meter square. Now required length of footing. So for general cases, we consider a square type of footing so that there will be equal pressure distribution. So considering a square footing, square root of this 1.72 will give this required length, that is 1.31 meter. Similarly 1.31 meter, that is the width. Generally the value should not be less than 1.5 meter considering the real field practices. So we can take this value as 1.6. We get the area of footing 2.56 meter square, which is greater than 1.72 meter square, hence it is safe for bearing. Now we will model this isolated footing on SAFE with these dimensions. Rename it as column reaction. Self weight multiplier 0. You can keep this as 1. It won't be any difference. It won't make any difference. Okay. Similarly, load case, it will be, you can just rename this column reaction. Okay. Design, so we have to edit over here, design preferences. So we have to make this as IS 456 2000. Similarly, load combination, add new combo. You can add two types of load combo, or you can go for the default design combos. And here you have strength ultimate, service initial, service normal, service long term. So the strength is as the limit state of strength, so we have to check it for the ultimate condition, and limit state of serviceability for the initial condition. So you can untick these two. Okay. Modifier, so combo, here you can see UDCon 1, dead load and column reaction as 1 1. So this is the initial service service. So the scale factor is 1, it is okay. And similarly for now it will be 1.5 as per IS code. So this is strength. So these are the two load combination for which we will design the footing. Let us model the footing. Go to add or modify grid data. Let us add any random grid and model the footing. So grid data as A, B. Similarly in y-axis 1, 2. Here you can display grid data as ordinary spacing depending upon your ease. So similarly 0 and 1. Okay. And there won't be any Z data because for footing we will analyze it in XY plane only. Okay. So a grid has been modeled. Now let us model the footing. So you have three different options to go with. You can either draw slab or areas by point to point, or you can draw a rectangular area, or you can go for a quick draw slab area that is within the grid, or you can just quick draw areas around points by considering the dimension. So for isolated footing we can go for this. And type of object slab, the shape of object rectangular slab, property whereas we are going to model a footing, so footing 400, dimension we have computed as 1.9 and similarly 1.9. Now let us click at any grid, then we can draw footing that is equal to 1.9 and 1.9. You can directly model anywhere at the grid without drawing the grid point as well. Now we have to model the stiff as well, so for which we can go with the quick draw option, and here you have to select stiff, and the dimension should be equal to the dimension of the column, because as I said, the stiff region is between the joint of column and the slab. So considering the column size at 0.3, that is 300 mm, so the stiff has been modeled as well. Now we'll assign the subgrade type, that is soil property, assign support data soil properties, and you can go for soil 1, and you can see that this soil modulus has been assigned. That is a type of support that will provide it to the footing. Now we'll assign the load data, that is the point load that is coming from the column base, and for which we can go for assign and load data. But as we haven't drawn any point over this region, so we cannot apply the load directly. So we have to go to draw, and here we have draw point, select this intersection point. Now the point has been drawn, then you can assign the column load. Select this, assign load data, point loads, and we are going to assign a column reaction, and the load is to be applied in the direction of gravity, which was equal to 172 kilonewton. So 172 kilonewton. You can either apply moment. Okay, let us take the moment as well. So mx is 3 and minus 256. So let us take this as 4 and another as 3. Round up value minus 3. Size of load for punching shear. As we know, the punching effect is due to the penetration of column into the slab, so we have to enter the size of the punching load or the area of the punching load, so which is due to the column, so we'll apply the size of column 300 by 300 mm, so it is in mm. So if you want to add to the existing load, there is no load in existence, so for now we can go for existing load, but generally replace existing load will be a better option. Okay, so if we see in 3D, you can see that the load is being applied. Let me unview the grids. So minus 3, 4, so these are the moments. Let us go to XY again, undeformed shape. So for the slab analysis, that is reinforcement calculation, we have two approaches. One is finite element method and another is strip based method. So for finite element method, we don't have to do any extra, but for the strip analysis, we have to add strips along both direction. So now for strip based analysis, let us add strips. So for this, go to draw and draw design strips. And now the strip should be designed in such a way that it covers the whole area. So we'll consider the midpoint of this footing and we'll draw a strip at the mid in both direction such that it covers all the area. Strip layer A. So considering this layer as A and this as B, so start with left 1.5, start with right, end with left, end with right. So we are considering 1.9. So start with left. So from the left, 1.9 divided by 2, 0.95, 0.95, 0.95. So the strip has been drawn. Similarly, B, like this. You can see the area which this strip includes. So for this, go to display option, and here you have show width, and now Okay, so you can see that the strip has covered all this area. So if you remember, while defining the slab properties, we have just included the slab material, that is M20, but we haven't fixed the rebar material type. So for the reinforcement designing, we have assigned or we have drawn the strips. So right click on this, if firstly select the strips and right click on it, and you can see here strip design type column strip. Okay, rebar material, so here we have to select rebar material as FE500. Okay, and similarly in this direction as well we can select as 500. Okay, now let us run. So the very first thing after running the analysis, we get deformed shape, displacement, dead. So this is the settlement due to the dead load, but we have to check it for the service load, that is dead load plus live load. So display show deformed shape, we'll select load combination, and including service it will have the dead load of foundation plus the reaction coming from the column. Apply. So we have minus 3.98 and minus 468. These are the maximum and minimum value for the deformation, or we can say deform shape or the displacement. And the allowable settlement for the isolated footing is 25 mm, so it is okay. Secondly, we can check for the swell pressure under the footing, and for this also we have to check for the service load condition. So select swell pressure and apply. We have minus 52.54 kilonewton per meter square and minus 61.9 kilonewton per meter square. So those value are less than 110 kilonewton per meter square, so it is okay. If the swell bearing pressure is exceeded than that of the allowable value, then we have to go for a greater size of foundation. But in case of poor soil condition, where the bearing capacity of the soil is very less, such as sand, then we have to go for deep foundation such as pile foundation. This pile supports the structure by the skin friction between the pile surface and the surrounding soil and end bearing force if such resistance is available to provide the bearing force, and accordingly they are designated as a frictional or end bearing piles. Now let us check depth of footing is sufficient for the punching shear or not. So this comes as 0.1564. So basically this is punching shear capacity by shear reinforcement. If this value exceed 1, then we have to provide shear reinforcement in slab. And for general footing or slab, it is economical and easy if we avoid shear reinforcement. Now finally we will design the slab, that is reinforcement for slab. So for which we have design basis as strip based and finite element based. So starting with strip based, layer A. So this direction is the layer A, that is direction X, and direction Y is the layer B. So top rebar, so bottom rebar, and field diagram, so value at controlling station diagram. Okay, let us select this, and we'll impose the minimum reinforcing as well. So that is basically the minimum reinforcement considered for the design of a slab considering IS 456, that is 0.15 times of gross area of section. So firstly select layer A, apply. So in this direction the maximum reinforcement is 600, and basically this is due to the minimum reinforcing. So if we do not impose minimum reinforcing, then we will see a smaller value, that is 205.969 mm square. So this is the maximum reinforcement required along this direction due to the loading actually. As we know, we are calculating the reinforcement according to the bending moment at the edge, considering this as a cantilever portion. So this is the reinforcement. But if we impose minimum reinforcing, which is necessary to impose considering the temperature reinforcement as well as the minimum reinforcement criteria, we will get 600 mm square per meter. Similarly, layer B, it is also same in this direction, that is minimum reinforcement is dominant. Let us calculate the number of bar and the spacing required. So considering minimum reinforcing in either direction, the reinforcement is 600 mm square. So considering unit width, so 1000 mm divided by 600 mm square into considering a 12 mm bar, the area of 12 mm bar is 113. So we get 188.33 mm. So this is the spacing required. We can opt for 150 mm, that is 12 mm bar at 150 mm center to center spacing. Similarly, in this display tab you have shear reinforcement, and you can check for it, and it is 45.186 mm square per meter. So this is very small value, so it can be avoided, and the shear strength of the concrete is sufficient for the shear force. Now there is finite element based as well. Impose. So direction 1, direction 2. So simply this is the local axis, and you can find that in the display option. Control W, turn on the local axis. Okay, so on deform shape, let me turn off the show width. Here you can see red color is the local axis 1 and the green is local axis 2. So direction 1 finite element based, apply. So this is the reinforcement along direction 1 in top side. Similarly direction 1 bottom side, we have 600, that is due to the minimum reinforcing. Let us untick this and apply. So you get 273. Similarly direction 2 top rebar and direction 2 bottom rebar. So there will be certain difference between the area of reinforcement calculated by strip based and finite element method. So you can choose any one of it considering the design approach. So this is about the reinforcement calculation for the isolated footing. So when the load is subsequently less, or we can say when the loading of the column is normal and the space available is sufficient such that there is no intersection of the isobar under footing, then we can go for isolated footings. Here you can see in this condition also I have provided isolated footing because there is sufficient gap between two columns and the loading on the column is also normal. But in some cases you might have seen a slope type footing as well in this way. So this is provided when there is no need of top reinforcement, that is only bottom reinforcement is necessary. So we can select this type of footing and we can save the quantity of concrete as well. But make sure to give certain projection like this, that is the offset on either side to support the formwork, and generally it should be provided at least 100 mm on either side. So this is how the isolated footing is constructed in field. And this depth, that is the depth at the edge, which is also known as edge depth, should be at least 200 mm. So we can just transform this isolated footing into this by removing the extra concrete if there is no need of top reinforcement. And generally top reinforcement is not necessary in isolated footing because isolated footing or the top reinforcement is provided when there is earthquake reversal effect, but it will be necessary for a combined footing. Why it is necessary, we will discuss that later on. So this is the AutoCAD detailing of the pad footing, that is without any sloping surface. So this is the plan of the isolated footing, bar A and bar B, and generally for a square footing the reinforcement is provided same in both direction, in our case which is 12 at 150 mm center to center spacing. So here you can see D being the overall depth, DF that is the depth of foundation from the ground level. This generally it is provided as 1.5 meter considering frost action. These are the column rebars that goes into the footing up to a length LD, and bar A and bar B that are the reinforcement for isolated footing. So as I said, we generally don't provide top reinforcement. But regions subjected to earthquake reversal effect, we can provide top reinforcement as well, as you can see in this video. If we are providing isolated footing with sloping surface, then it looks something like this. So as I said, we will provide certain offset, and that should be at least 100 mm, and the edge depth should be minimum of 200 mm. Now let us see a case for a isolated footing that has to be provided with a strap beam. So here you can see this is an isolated footing, this is also an isolated footing, but it has been connected by a strap beam. So this becomes necessary when the loading on the column becomes eccentric. So here you can see that the column is concentric, that is the load is being applied at the center of the footing, but in this case the loading is done in eccentric approach because due to property restriction, as there is no land available beyond this point, so the column or the footing for this column becomes eccentric, and in such cases the eccentric footing should be connected to a concentric footing with help of a strap beam. In many cases you might have seen that for a eccentric footing there is no provision of strap beam, and that is a wrong practice because without a strap beam this footing undergoes bearing failure. I will show you that in this video as well. So now let us model a strap footing. So let us take the load of these two columns here. So now let us design for these two columns that is 303, 227. These are the loadings, and if you see that I have provided isolated footing in this direction and two strap footings in this direction, but two combined footing in middle. So this is due to the reason that you can see here the loading at center is more, 435, 401, and at the edge we have 260, 303, which is less than these two footings or these two columns. So I have provided combined footing, and I will show you why I provided combined footing over here. But first let us do with this. Now let us unlock this. Let us delete and go to modified grid system. So along x direction we have to add. So let us take the distance. So it is 3.6 meter. So let us add 3.6 in this direction. Okay. So grid. Now let me draw a footing of size 2 by 2. But this is eccentric with respect to column. Okay, let me draw first column as well. 0.3.3, and it should be stiff. I have to move this, so it is minus 0.15 and this is minus 1. So let me move this in x direction by 0.85. Okay, so here you can see it is now at the edge. Now if I apply load at this point, let me draw first points over here and over here, and select the points, assign load, which was 227. We'll take the maximum one, so 170 and 227. So we are designing for this two columns, so 227. Assign load data, point load, we'll select column 270. Is it? No, 228. Okay, and dimension of the punching load, so 300 mm by 300 mm. Apply. Similarly for this we have 304 replace. Okay, so we have applied the load, and let us assign the subgrade modulus as well. Soil properties, and okay. Now without providing strap beam, let us see the reaction. So let us check the deformation first. Deform safe, load combination, and apply. So you can see we have a increase in the settlement, and you can see in the 3D as well. So the load which is at the one corner has caused the deformation, that is settlement, excessive settlement over this point, and this is due to the eccentric loading, and the provision of strap beam reduces this type of settlement as well. Now let us see for the swell pressure, which is the major cause that we are providing, or which is the major reason we are providing a strap beam. Load combination service, apply. So you can see that swell pressure is minus 179.01, which is at this point, and you can simply understand that the load is being localized at one corner and it cannot be transferred through an area, as because there is no projection beyond this point. So the swell pressure will be excessive at this point. Hence we have to assign, or we provide strap beam, and hence we cannot provide a centric footing without a strap beam. That is a very wrong practice. Hence we have to provide a strap beam to avoid such failures. If we see through the slab reinforcement design, then it won't be a problem. If you see here, let us go for this finite element, apply. Here you can see the reinforcement is 672. It is easily satisfied by 12 mm bar at 150 mm center to center spacing. There won't be a problem. The problem lies with the bearing failure. So we have to consider that case. Now let us introduce a strap beam. Define beam properties. We'll modify that only. So property name beam 1, okay. Beam material M20, rebar material FE500, rebar material for shear as FE500. We'll provide a rectangular beam. I have also uploaded a video for design of strap footing manually. You can check it out and understand throughout the theory and assumption we make for the design of the strap footing. Wave width at the top, so let it be as 300 mm. So we are just considering at least size equal to the, or beam of size of the beam equal to the width of column. It can be greater than the size of the column as well, depending upon the requirement. So for now 300 as we are considering a rectangular beam, so 300 by 300. Depth, let us take as equal to depth of footing, so 400 mm. Clear cover to center 50 50, okay. XY. Now let us draw the beam from the center point, and we have to provide a projection as well, because it will be difficult to take all the rebar into the column, so it will be easy to extend that beyond the column. And let us go to draw design strip 0.95, okay. For now we have provided 2 meter, so it should be 1 1 1 1. Okay, it was for B. Now let us do for B first, that is in Y direction, and similarly in A. Now you can go for show width and see the strip area, it is okay. Now let us run. Firstly, let us go for the 3D view so we can easily understand the reduction in the displacement. Load combination, service, apply. So as you can see, it has reduced due to the inclusion of the strap beam. So which was minus 13, now it is minus 8 only. Similarly, go to soil pressure and apply. So it is minus 105.74 kilonewton per meter square. So it is within the range. Now let us see the punching effect as well. So it says not calculated. So when there is provision of strap beam, punching shear calculation is not shown for the footing, because as the beam consists of the shear reinforcement, that is the stirrup, so it is responsible to resist the punching effect. So we saw NC, that is not calculated. Now in case if I apply load on column, for example let us assume 200 without size of the load for a punching shear, that is 0 mm. Then now let us uncheck this and let us delete the strap and run, and then see for punching. You can see that it will show for this because we have applied punching dimension, but for this column we haven't, or for this footing we haven't applied the punching dimension, hence it won't show the punching shear capacity ratio. Now let us go for the reinforcement. I find strip based more easier to work with. Apply. So the reinforcement is 749.013. Impose, that won't be any changes because 600 was the minimum reinforcement required as per IS 456, but as per the moment we have 749, so 749 mm square per meter. And I have already shown you, you can compute the reinforcement required as 1000 divided by the reinforcement required 749 divided by, or we can just multiply it by the area of the rebar chosen. So for now 12 mm bar, so it comes as 150. So we can provide 12 mm bar at 150 center to center spacing. We have also provided a strap beam. So now let us see the reinforcement for it. You have strip force, beam design over here, or you can also go here and see the beam design. Select over here, and you have longitudinal rebar, impose minimum reinforcing, field diagram, so values at controlling station, so it will be easy to understand. Apply. So we have 1146.709 mm square. So this is the reinforcement required at top, and at bottom we have 359.614. For the hogging moment, that is a negative moment, the longitudinal rebar at top will be more than that at the bottom. So we are having maximum reinforcement at top, which is 1146.709. So if we provide 16 mm bar, if we are considering 16 mm bar for the reinforcement, and for 16 mm bar the area of individual reinforcement will be 201, and for 1146 that will be a 6 number of bars should be provided. So 1206, but 6 mm 6 number of bar will be a little bit difficult to arrange inside for at the top section only. So we'll select 4 numbers of 20 mm bar, and for 20 mm bar the area of reinforcement is 314, so 1256. So we can provide 4 number of reinforcement at top, and similarly at bottom we have 359, so we can simply provide 4 number of 12 mm bar. So for 12 mm bar it is 113, so we get 452. And similarly for transverse reinforcement we have 738.199 mm square per meter. So we have to calculate the spacing of stirrups and the size of stirrups. I have made an Excel sheet for it. Okay, let us take this Excel sheet for our example. So area of longitudinal reinforcement, which was 1146 and 738 as the shear reinforcement. So we are assuming to provide 20 mm bars, so we'll get area of steel as 1256, which is okay. Or we can go with 2 and 3 numbers of 16 mm bar, that is also okay. Now for shear reinforcement, design shear reinforcement, which is 738. So depth of beam, which is 400 for now, and width of shear critical region is 300, that is width of beam. And number of legged stirrups is generally 2 legged stirrup for residential building. Stirrup diameter 8. Area of shear reinforcement 100.53, that is if we consider 2 number of legged and 8 mm stirrup, then it is equal to 2 into pi d, that is 8 square by 4. So spacing required is equal to 1000, that is unit width, divided by 738 into 100.53. So we get this as 136.22. So spacing provided you can take as 125 or 100 mm depending upon your site practice. So for now I am taking 100 mm. So finally provided shear reinforcement of the section will be 1000 divided by spacing provided into area of the shear reinforcement. I have made a complete video for the calculation of shear reinforcement in beam. You can check that video as well. I have also shown you how to prepare this Excel sheet. So in this way the strap footing is designed. Now let us see the combined footing case. Before that I will show you why I selected combined footing at this region. So while calculating it manually, we are assuming uniform pressure distribution under the footing. So it is necessary to provide equal width of the footing, but the length can be different. So now let me show you here. Let us reduce the footing size. It won't be a problem in this case. So still it is minus 103.42, because it was at this point, at this region. It is a normal case. That is the footing is concentric and it has whole area to distribute the load, and there is uniform pressure distribution. But in this case the load being eccentric and there is no projection beyond this point, hence the pressure gets concentrated at one end while other end has a lower pressure. Talking about strap footing, so we have provided strap footing over this section and over this section. Now let us see the rebar detailing. So this is the rebar detailing of strap footing. As you can see here, this is the plan and this is the strap beam. The hidden line is the footing provided and continuous line at the top is the strap beam. Sizes are different than that of the value we have just provided. And similarly for number of 20 mm bar, and we can also provide face bar for the beam size exceeding 450 mm in order to avoid torsion. So we have provided a complete bar throughout the beam, and 4 number of 20 mm bar at top and 4 number of 16 mm bar at bottom. Let me compare it with, so this is the isolated footing and this is the isolated footing as well. So this is the isolated footing as well, and if we see reinforcement for this case, the main bar is placed along this direction. But in case of strap beam or strap footing, the reinforcement or the main bar are along the transverse direction. Now let us see for the higher loads, 435 and 335. The spacing is same, only the load is to be changed. Assign load data, point load, Coulomb reaction 335, x dimension, that is size of load for punching shear, is same. Remember to keep replace. If we add, then it will be 228 plus 335. So okay, 3D, you can see 335. Similarly here we have 435. So the load has so you can see 739. This is what I was talking about. So we have to do replace. Okay, now let us run. Apply. So you can see the bearing pressure is minus 147.29 kilonewton per meter square, but the safe bearing pressure is 110. So the value has exceeded the permissible range. So we have to increase the footing size. And similarly, if we see the beam design, we have 1702. That means at least we need 1702. So that means we require 6 numbers of 20 mm bar. So it will be difficult to cast 6 number of 20 mm bars. So basically we are assigning 6 numbers of 20 mm bar at the top only. So it will be difficult. Either you can increase the size of beam, then for a general isolated footing considering a load of 300, okay, 335, considering soil bearing capacity as 110 kN per meter square, the size of footing required would be 1.9 meter, because the area required is 3.35 meter square and required length will be 1.83, but we are already providing 2 meter width on either side, but still it is not satisfying the bearing condition. Hence in such case we have to opt for other type of footing, because it will not be economical to increase the size of footing beyond certain point. So we will opt for a combined footing. So that is why I provided combined footing in this case, because the area covered by a combined footing is much more greater, and hence there is chance that the bearing pressure will pass. Let us select the footing, go to plan mode, let us delete this, and similarly the beam as well. So firstly let us see without providing any projection on this side as well. Now let us draw this strip again. A, so start with left, start with right. 1, let us see the width, so it is okay. Similarly let us draw for the other direction, draw design strip. So now for this direction we have 1.8 at this midpoint, so you can see over here 1.8, and this is from this point, so we have to add this point as well. So 1.8 plus 0.15, 1.95, 1.95, 1.95. It is okay. Now let us run. Firstly let us see the deformation for load combination service. So it is minus 11. It is still within the range. Now let us check for the pressure first. Apply. So it is minus 155. So for now you can see the load is concentrated at this point, so we can extend this side because we are allowed to do that, because we have area in this side, if you see. So let us project this side. Okay, now let us Control W, let me uncheck soil support so it will be easy to understand, and let me uncheck the local axis. So I need to extend this side, So what I can do is just I will select this edge only and then go to edit areas, expand or shrink areas. Let me extend this by 500 mm. Okay, and we'll check it again. Let's go to soil pressure, apply. So we are done with this side, but the reason at this point is still critical. We can extend this point. Now let us extend these points by 200 mm on either side. Okay, and now let us see. So here you can see the pressure is now minus 100.64 kilonewton per meter square. That is within the range. Similarly, punching effect 1.3 and this is 0.4352. So that means as the value has exceeded 1, there is requirement of shear reinforcement in the slab, which can be avoided by providing a beam between these two columns so that the reinforcement or the shear is taken by the beam, or we can increase the size or depth of the footing. So firstly let us increase the depth of slab properties, footing. So now let us take this as 550. Okay, and similarly stiff also 550. Now let us run, and so 0.805. So this is okay. Now as the shear strength of the slab increases with increase in the depth, so it is safe against punching shear. Let's go for slab design. So we have reinforcement as 660. I think that is due to minimum reinforcement. So if it was not provided, then maximum reinforcement, which will come at top, as I said, due to the hogging moment, that is due to the soil pressure, which tends to push the slab upward, and at bottom we have 155.69. Similarly, layer B, that is along this direction, which will be less in comparison to the longitudinal direction. Let us calculate the reinforcement. So we have 642.391. So we can just provide 12 mm bar at 150 mm center to center spacing. So that will give us 1000 mm unit width divided by spacing provided 150 mm for 12 mm bar, which has area of 113. So we get area of reinforcement as 753, which is greater than 642. And if we impose minimum reinforcement, we have 660 mm square per meter, which is still in the safe side. So we can provide 12 mm bar at 150 mm center to center spacing. Similarly, this is the detail of a combined footing. The main reinforcement is provided along longitudinal direction. So you can see 16 mm bar at 150 mm center to center, and the transverse reinforcement 12 mm at 150 mm center to center spacing. So just try to understand the reinforcement detailing of this drawing. So similarly in cross section, as we can see, the longitudinal bar are provided as the main reinforcement and the transverse reinforcement is provided as the secondary reinforcement. So in this way we can provide a combined footing. So the case where combined footing is provided is when the two columns are subsequently close to each other, when the loading on the column are subsequently greater such that the isolated footing becomes uneconomical, and even in the case of strap beam where the sizing of footing arrangement becomes uneconomical. And so as you can see here, I have footing F5 and F4 with dimension of 2000 and 2150, but there is a chance that the isobar of these two footings may overlap with each other, and it was modified into a combined footing so that there won't be any issue regarding the overlapping of isobar, and it will be difficult to cast as well if there is very less space between these two bars. So I hope you can understand now why I provided a strap footing, why I provided an isolated footing, and why I provided a combined footing. So in case if there is two eccentric column and a concentric column at middle, then we can go for this type of strap footing, and in case if it doesn't satisfy the bearing condition, then we can go for a combined footing considering three different columns. Now we have another type of footing as well, that is mat type. So here you can see I have provided strap footing on all cases, but I was not able to provide strap footing for this case, and the reason is a little bit different. So this is my property area, so I cannot provide footing, or I cannot provide or construct any structural components beyond this. If I will to provide a strap beam over here or a strap footing here, the area of the footing will go beyond this, so it is not possible to construct a strap footing for this column. It could be possible for this. So as you can see, I could just, let me hide this object, let me assume this footing, and I'll take, so here you can see it was possible for this, but it won't be possible for this because it will come outside the site area and that is not allowed. So what I have to do is I had to provide a mat footing, because combined footing cannot be provided, sorry, a strap footing cannot be provided in such way, because the simple idea is that to distribute the pressure throughout the area available, and for such case both of the footing would be eccentric and there is no any chance of this footing to pass in the bearing check. But what can be done is, if there is a central footing in middle and eccentric footing on either side, then these two footings can be connected through strap beam with the central one, what I have done in this case. And again, if the footing or the loading increases, that is for the interior column, the loading will be more than that of the outer one, so I have provided a combined footing for this. So now we'll understand how to design a mat footing. So I hope you got the point why I provided a mat footing for this column arrangement. And one problem we will have in this type of mat footing is that there is no any air in this and in this region to extend if there is any type of failure, and if it doesn't pass, then we have to go for a piled footing. That is, the mat footing will be accompanied by some pile that will reduce the bearing pressure. So now let us model this first. Now we have to make a proper grid. Right click, modify grid 3.6, and let us assume in y direction as well 3.6. okay, so this is basically the distance between column. So I'll draw column 0.3, 0.3, and this should be steep. Now let us extend. So firstly we'll check without any projection, and we'll see if there is necessary to offset the edge or not. Let us draw the point first, and we will apply the swell support as well, swell properties. As the site is different for this building, so the swell pressure here is taken a little bit different. So the swell pressure or the safe bearing pressure is considered as 130 kilonewton per meter square. Okay, and if we have assigned or if we have provided grid data properly, then we can use auto design strip. So add design strips, add design strip along Cartesian grid line, include middle strips, and using auto, and for x direction that will be A. Okay, so you can see, and similarly edit and go for add a design strips and Y B. Okay, so this was the case in which I provided a mat footing due to the property restriction. So now let us see the reaction. 308, so we'll apply load accordingly. Assign load data 592, and this is 350 for the case I have done. Okay, so 18 mm it is okay. Deformation. Now let us see for the base reaction. So this comes as 239, so we have to increase this, for which Let us go to plan mode. As we cannot extend this side and this side, so we'll extend these edges. Let us see the bearing pressure now. Here the soil bearing pressure is 122, so it is less than 130 kN per meter square, so it is safe. Now let us check for, so this is 1.0639, so we have to increase the depth of footing. Let us take 650, similarly stiff also 650, 0.9, so it is less than 1, it is okay. Let me extend this. Okay, now let us go for slab design. Apply. So we have 1061.167 mm square per meter. So let us see, 1000, that is unit width, divided by 1061.167, considering 12 mm bar. So the spacing is 106.48 mm, that is 12 mm bar at 100 mm center to center spacing. Or we can go for 16 mm bar into 201, that is area of 16 mm bar, so we get 189. So 16 mm bar at 150 mm center to center. For bottom as well, 975, we can go for 16 mm bar at 150 center to center spacing along this direction. Now let us see for layer B, that will also be same, so 1095, 975, so 16 mm bar at 150 mm center to center for both directions. So that will be the reinforcement. As you can see, this is the plan of the mat footing. 16 mm bar at 5, so this is in inch, so 15 mm bar at 5 inch center to center, and similarly 16 mm bar at 5 inch center to center along this direction. So this is the cross sections. This is somehow similar to that of the combined footing. So here you can see 16 mm bar at 3 feet 3 feet spacing. So these are the shear reinforcement that supports the reinforcement before concreting. So to hold the reinforcement, it doesn't have any structural importance, just to hold the reinforcement in its place. 16 mm bar at 5 inch center to center, top and bottom, and 16 mm bar at 5 inch center to center, top bottom. So this is the bottom mesh, this is the top mesh. And according to the municipal provision, either you can provide tie beam or you can just go with the plinth beam only. The basic idea of providing plinth beam and tie beam is to connect all the columns at a certain level. So if you are providing plinth beam, then it is not necessary to provide tie beam, but this is a general practice that has been followed by municipality. So still we are providing plinth beam and tie beam when there are certain vertical offsets within the mat footing. So there may be a footing like this, footing for our house, and you can see there are certain offsets provided according to the requirement. So let me show you the safe model for this as well. Here you can see this is a machine foundation with certain vertical offsets provided as per the depth required. So I'll show you how to provide vertical offset, then you can understand how to draw this type of footing as well. Okay, let us see how does it look in extruded view. And these are the punching, or that is the stiff section provided. So now let us consider a footing, and let us select the property as a new type, add copy of property, providing this as 300 mm only. Okay, so let us consider the footing depth required at this side is smaller. So as you can see, the depth is small. But what if I have to provide this footing at this level, that is the starting level for both of these footing should be equal. Then for this, just select this footing, right click on it, and here you have a vertical offset, and give the magnitude by which it has to be shifted downward, or the vertical offset. So minus, basically the depth of the greater footing is 650 minus, and the footing which we are considering is 300 mm. So this is the difference, and that should be negative. Okay, okay. So here you can see the footing has been provided with the same vertical offset. There won't be change in the bearing pressure because the bearing pressure depends upon the area of the footing. If we provide footing at the top level or at the bottom level, the area will be same. So I hope this video helped you, and if it did help, do like and subscribe, share with your friends. Thank you.